I am using my phone to connect to internet. The server is still not completely alright, but I guess that's because of my end. Okay, it's getting better. Okay, the streaming is on, so it's, how is it?
I can't say yet.
Is it that, so what about you? Are you able to see the streaming?
I'm not trying.
I mean, can you check how is the streaming? Is it all right?
You can check.
It seems that it's all right because I've been on already like 10 seconds or something.
Yeah, my internet just is slow right now.
Okay, so you cannot tell.
No, it's okay.
So it's okay. How is my voice? Am I, so let me ask this, am I understandable? Okay, so one more thing that is missing is that we need this to back on. So for online participants, I would like to apologize that we have a little bit of issue with the internet connection. Seems that for unclear reason, the other one is very slow today. So that also will affect you guys today, because if Ethereum is slow, it means that you will have a difficulties to enter your answers in Socrates. But we'll see. Let's worry about that a little later. So, so we're a few minutes behind the schedule, and I hope that soon all the practical matters are solved. We're ready to get started. So let me just, okay, so projection is on. So we're very close. So what about my YouTube officer? Can you check that my voice is all right? No comments? What about, is there any comments from the, can you please check from the YouTube if there's any comments from online participants, complaints about my voice or something else?
I can see that.
You cannot see anything. Okay, any comments from online participants, like how is it they hear me? That comes with a significant delay, so we need to wait a little while to hear their responses. So, so that's the mic check back there.
It's working.
So it's working. Awesome. So, simulation of a mechatronic machine, lecture number 10. Respect. You ready? Okay. So. Today, what will happen is that we will continue to discuss about modeling of hydraulics. And what is going to be the major objective today is related to modeling of hydraulic components. Because so far, it's been about what are the mathematics needed in a hydraulic modeling, but we have not touched about the hydraulic components. And this is what we're planning to do today. Right after I have explained about how about the flow times. But prior to entering the modeling of hydraulic components, I have quite a bit of extensive explanation related to summary what we did last week. Because I believe that I missed something quite important last week. And also I got the feedback from some of you. And in that feedback, there was a clear typing mistake that I would like to explain. And that typing mistake actually happened 2 weeks back, 3 weeks back, 2 weeks back. So that's what's going to happen today. So I guess we are ready to get started. This is the typing mistake that happened 2 weeks ago. So I was wondering when I explained this embedded technique, many of you were really surprised, like really disappointed to me. And now I know why was that. Because obviously what happened was that you were able to pinpoint the typing mistake in my slide. You were so confused because of that, not because of the typical topic. So you were like, oh please, Isaki, so he's just keep on making these typing mistakes. So maybe I should leave, or I'm not comfortable with this. And I could tell that from your face. And then later you came back to me and said, the problem in my lecture was that there was a typing mistake, obvious typing mistake, because when you look at my slides, I have here this component that is incorrectly typed. Can you see what's the problem? Here what I have here is a takeoff matrix multiplied by what? Acceleration of generalized coordinates. And of course, it should be velocity. So that was the thing that makes you confused, correct? That was all the time in your mind. How is your sleeping? Have you been able to sleep? No, yeah, I thought, yeah, that's what I guessed. Yeah. So it's all because of this. But now you're safe. You're safe. Okay, so this what that's supposed to be is Jacobian matrix multiplied by velocity. And actually I'm very serious about that. I would like to give a credit to the students that I was able to pinpoint that, and I will. But because this is YouTube streaming, I'm not allowed to mention the name of the student, but I appreciate this, and I will find a way to give you extra credits because of this. So if you see the mistakes in my slides or my lecture notes, please let me know. So I will try to give you something back to you. Okay? Then there was another problem in my slide, and it was related to this matrix CD, because in a matrix CD there are two typing mistakes. So first of all, they're supposed to be minus before this vector, which is differentiated twice with respect to time. And then there's the same problem related to Jacobian matrix multiplied by what? It's supposed to be velocity, not acceleration. So the right typing is the one that is on here. So that's how it's supposed to be. Okay, so that happened 2 weeks back. Now, quite extensive summary what we discussed last week. First thing the obvious thing that I did not mention here last week was that here in the hydraulic modeling we are using the drawing symbols. And now, if you're uncomfortable or if you're shy with the drawing symbols, this is something that you must do by yourself. So you need to go and log into online, some of the web pages that explain what are the drawing symbols, what is that they stand for. Because in reality, this is how the hydraulic circuit look like. But of course, we are not going to use that kind of three-dimensional drawings to explain how the hydraulic circuit, but instead, we're using the drawing symbols. And now, if you don't know what the drawing symbols, what they are standing for, this is what we will not explain in this class, but you need to just catch up by yourself. Just, an example. In reality, we have an electrical motor here. An electrical motor in reality looks like this. And the drawing symbol associated this is just a motor. And then we have a pump. And the pump is described by this drawing symbol. And then what else we have here? So we have here pressure, direction valve here. Direction valve is the one where the drawing symbol is shown like this. And then we have the symbol valves here. They are the ones, this is this one, and this is this one. That's how they look like. And this is finally the pressure relief valve that takes the flow back to the tank. So that's the way we describe it. I mean, this is the way we're describing the hydraulic circuit. Okay? So then last week, we discussed about the properties of liquids. We concluded that for us, the most important thing regarding the properties of fluids is about modulus. Bulk modulus is something that there is a 99.99% certainty that you can find a question related to bulk modulus in the next midterm exam. And the next midterm exam is within a few weeks. So I will ask something related to bulk modulus. So the bulk modulus describes the flexibility of flow. And there is this week weekly homework that is related to flexibility of flow. We will get back to that within the next slide or so. Okay, how is that we can describe this flexibility? It actually consists of number of components. So we can first of all describe the flexibility of oil, and then we can describe the flexibility of different containers. This is a flexibility of the container number 1, this is a flexibility of container number 2, and this is a flexibility due to the dissolved air. And you just keep on adding these components, and all of these components will affect how stiff or how rigid is a hydraulics. So that's something that you do need in a hydraulic model. All right. Then in this week weekly homework, there is a simple assignment such that I'm asking you to calculate the natural frequency associated to grain that was like the simple crane that was operated by hydraulics, and there was a hydraulic cylinder here, and a mask like that because of the flexibility of hydraulics. What will be the natural frequency of this system? And natural frequency you can compute if you know the stiffness and the mass. Okay? So one of the important things here is that first of all, if you know that the mass is ended here, on this free end of this simple crane, you have to convert the mass to be applying here. And I think that the numbers were provided in such the way that it was quite straightforward. If I remember correctly, this length was 0.1 and this length was 1. So meaning that the mass applying in the end of the crane will be, the mass here, whatever it was, mass multiplied by 10. And where the 10 is coming from, that's coming from the, these lengths. So it's 1 divided by 0.1. So that's going to be, this one will be 10. But what about the spring coefficient? How is it you can compute that? And now this is what I believe that I skipped last week lecture. Did I not? I skipped. Look, my memory is extremely strong, but it's a little short. And this is, thing that, it was still, even with this condition, I remember that something was missing last week lecture. And then I did not watch the recording, but I was checking from the slide. Was there something that I skipped? And this was the particular location that I skipped. And with the information that was provided last week, it will be very difficult for you to accomplish the weekly homework. So let me explain this. So how is it you can compute the weekly homework? And this is exactly the 2 slides that I skipped last week. Okay. The aim here, what we really wanted to do is that we wanted to compute the stiffness here that is associated to hydraulics. And we already mentioned that there's a bulk models that explains it. So how we can actually carry out this task? Well, first of all, we have to understand what is a stiffness. Well, that's a stiffness is something that is a relation between the force change and the distance change. That's what the stiffness is. So knowing this, so it's if you have curve in such the way that I have here force, the displacement. So this slope here, that's the one that defines the stiffness. Okay? So now using this information, we can start actually applying the concept. Let me take this one, the concept of bulk models, and with help of the concept of bulk models, we can actually define what's the stiffness of this particular setup here. And this is a two-way cylinder where there's a pressure applying here in a piston side and the pressure applying here in a piston rod side. Okay? So force difference. So how is that we can express the force difference? Here, if the force of force is a pressure multiplied by a corresponding cross-section area. Cross-section area will not change because we are looking at the cylinder that will remind that where the dimension and the geometry is not changing. So the only component that can change is a pressure. Now, here the pressure in the piston rod side, if you press in the piston this direction, it will actually decrease. And then the pressure in the piston side, which is this one here, that will increase. So that's how you can express the force difference. So it's a pressure difference multiplied by corresponding cross-section area in the piston rod side, and the pressure difference multiplied by corresponding cross-section area in piston side. Okay? How is displacement change? Because that's another component that we need here. Well, first of all, you may use the volume equation, which stands the area multiplied by position of the piston. That's how you can compute how much the volume of the, say, this particular section here. And the x here, okay, the x is measured here. But anyway, so this is how you can make it happen. And using this equation, you can express that the difference change that comes from the volume change in chamber number 1, this chamber here, and the volume change in chamber number 2. Okay? So now using this 2 information, I can substitute this here, and I can substitute this one here, and I can get the spring coefficient as it is expressed here. not get in a format that is useful to you, and not get in a format that you can solve this problem. But let me take a few definitions in my help, and then soon it actually becomes quite straightforward. You know, this is the equation that I got from the previous slide, the stiffness, and then I'm going to use this definition, how is a bulk modulus, and again I'm going to use a definition of bulk modulus as it is shown here. So I'm going to take the volume here, I'm going to put it in another side of the equation, so I have here pressure difference divided by volume difference, that's equal then the bulk modulus divided by volume size. All right? So now, substituting this information, this one here, I can get the expression as it is shown here. So the stiffness can be computed by such the way that I have effective bulk modulus in associated to this volume here multiplied by piston rod side area, or this area here, not the piston rod side, but this area divided by volume itself. And then here I have bulk modulus multiplied by corresponding cross-section area and the volume size. And I can simplify it as it is shown here. Now that's what you need. That's what you need in order to solve this week exercise. So you take K here, and in order to compute that, you need this effective bulk modulus. You can even provide, well, it doesn't really matter how you provide that value, and then you need the cross-section, two cross-sections and the corresponding volumes, and then you're ready to solve. And finally, the natural frequency, you can solve it by using this equation. Hold on. This equation. Clear?
Yes.
Yes?
How about the form in the right down the bulk modulus?
This one.
Yeah.
So,
And that's used.
yes.
Okay.
But, my recommendation here, because this is a numerical problem, I'm asking what is a number for natural frequency? That's what I'm asking here. So give me the number. Is it how many hertz?
Because I actually yesterday tried to do that, and I got do different answers because I used that, and I also determined the bulk modulus from the internet to be something like this.
Yeah, okay, so either way you will get the full points.
Okay.
So the question was for the online participants, because I'm not sure if it is this mic or this mic or this mic that is actually recording my voice. So if it is this mic, then the online participants cannot hear your question. So your question was clearly, where to get the numerical values for the bulk modulus? So should I compute it as using one of the examples from last week, or can you take a value from the internet? Either way, so you can get the full points. If you're using the values from the internet, then the recommendation is to use this something in this neighborhood, 100 to 1,500 megapascal, 1,500 megapascal, roughly in that neighborhood. That will be all right. It's actually, in reality, it's a little lower than that because if there's a hoses or something else connected, something soft component connected to the hydraulic cylinder, that will lower the effective bulk modulus. Okay.
There's a problem with the mic right now. There's an echo or something.
Okay. So that was a comment from online participants. Okay, so let's see. It's a problem in a mic. Okay. So whoever actually provided that comment, so as two different persons. So can we just wait a few minutes and see is it any better? It's supposed to be significantly better now.
Sorry?
So is it supposed to be significantly better? So online participants, please type. How is that you hear me? You hear me well, or are you still suffering from echo?
Now it's even worse.
It's even worse.
Yeah, it's really bad right now.
No echo.
Okay. Okay, so this is another test. So I think that I'm using now this mic here, this one. No, I'm not. I'm not using this mic.
It's clear.
So it's good now? So what is the response from
right
that?
now it's good.
So right now it's good. This is what annoys me a little bit. So it seems that every single time I have a little bit of issue with my voice. So I'm not making myself understandable to you. And even though that I'm using these high-end gadgets, you kind of still understand me. But if you can hear me, that's a good start.
Yeah,
So it's better now.
it's better. Yeah.
So the echo disappeared. Because I know that what you need to do later, not right now, but a little later, you need to go back and forth my recordings to prepare yourself to exam. And now if it is with echo, you're gonna catch migraine or headache at least. And then you will be after me and say, I'm scoring low in exam because I'm having a headache. And that's all because of the echo. Okay? But now we're here. So we're here. Oh my God, is this late already? So remember what the deal we made last week? That if I'm, if I'm not making this excessive explanations, you need to raise your hand and say, okay, that's it. So we heard these stories many times. Move on, please. So, okay, can you please raise your hand? Or maybe we can make another sign. So maybe if you raise your left hand with this sign, that's mean, okay, speed up, please. Okay, clear? Got it. Okay, so I'm gonna speed up. Yes, so, all right, so we're still in a summary of last week's lecture. So this is how we can compare the pressure at any given time and the components we have in this.
Lecture slides?
This way, okay? In this equation, so we have here pressure, so it's a P dot. That's exactly what we're gonna use in order to integrate the pressure. And then we have here effective bulk modulus. Then we have here volume size. We have flow rate in, flow rate out. That this is the change of the volume itself. Okay. So in this method, so what we're gonna do, we just simply gonna discretize the hydraulic circuit within the volumes where we are assuming pressure to be equally distributed. So what it means? So it means that if we have a damper like this, so we can make an assumption that the pressure, say here in upper right corner, will be the same as the pressure here in the lower left corner. And it is, because there's nothing inside of this particular volume that will introduce the pressure losses. But we cannot assume that the pressure here in upper part of the damper will be the same as the lower part of the damper. And we cannot make this assumption because there is something that will introduce the pressure losses. And what is the one that will introduce the pressure losses? This will be the trillings through the pistons. So those are the throttles where the flow have to travel back and forth. And typically they are introducing a little bit of pressure losses. That's why we have to use two different volumes in order to figure out the pressure this side and the pressure this side. And once we know them, then we can compare the corresponding force produced by this damper. Okay? Oh, that's a very unclear picture. So I'm not even trying to explain it here because I cannot see this even by myself. So this is a symbol. What is this? Is this a horse or? I don't know. I don't even know. What is that I have in my slide?
Fish.
What?
Fish.
Okay. So with that, we're ready to move on. So I guess that this is what something that you can find in my lecture note. If not, I will make this clear to you. Oh, by the way, I will make this clear to you because this my slides are available as a PowerPoint. It's going to be as a PDF in Moodle site. So please take a look at from that. I cannot explain what we have here just based on this particular slide. Okay, one more thing. So I have here an example how to use this first order differential equation. And in my example, excuse me. So in my example, I have here one-way cylinder, and in one-way cylinder, I have here a volume. Excuse me, the volume that is this size, and this cylinder is connected to a hose, and there's a flow rate that is coming into this system. I'm asking you to create the first order differential equation based on this information. Okay? So we are measuring here the distance of the piston by using an X, and the X is actually measured from the bottom of the cylinder, and it actually ends wherever the piston is located at. Okay? So now I'm going to use this information to compute to create the first order differential equation. So the ingredients that I need are, first of all, the volume, and the volume consists of two components. Okay, guys, you all clear?
Yeah.
So are you already planning what to do on Friday, or no, not at all? Something in hydraulics.
Yeah.
Well, good. Very happy to hear that. Okay, so what I have here, there is a volume equation. I have here the volume of the hose, and then I have volume of the cylinder. Volume of the cylinder is a variable. It's going to change depending on the piston position. So to compute that, I need to measure the X. And again, the X is starting here, and it ends where the piston is located. That is multiplied by cross-section area. That will be equal than the volume itself. Okay? Then the effective bulk modulus. The effective bulk modulus, I will have three components. The first that is associated to oil itself, the second that is associated to the cylinder, and the third that is associated to the flexibility of the hose. Okay, with this information I can calculate the effective bulk modulus, so I'm using the symbolic math tool to express it, and here it is. And I'm almost ready to move on to my, my differential equation. The final thing that I needed is how is the component that is describing the change of the volume itself. Of course, that's going to be the one where I have a cross-section of the piston multiplied by velocity. So that's what it is. Okay? So now, substituting the bulk modulus, the effective bulk modulus, that's going to be here, divided by volume size, it's going to be here, and the flow that is coming in. Now, this is extremely important that whenever you're modeling the hydraulics, you have to make a schematic drawing which tells you what is a positive direction of the flow rate. And that, by the way, was an idea of this slide, which is unclear. I'm trying to show that this is how you first supposed to make a drawing about hydraulics. In this drawing, you're telling, okay, let me try to explain this carefully. You're telling where the pressure is supposed to be computed, so where are the volumes, where the pressure needs to be solved, and more importantly, you must tell what is a positive sign of the flow rate. You can make this however you want. That's not the point. But once you make your decision, you must be consistent, because this is a typical mistake that you typically do when you do a hydraulic modeling. So when you compare, for example, when you compare the pressure here, P2, it's going to be effective bulk modulus 2 divided by volume size 2, and then this will be then, the flow rate here is coming to the system, so it must be positive inside. And then what is leaving is this one here, so is x2 multiplied by corresponding cross-section area. But the sign is actually coming from the schematic drawings. And you can make these drawings however you want. But once you do it, you must be consistent after that. Okay? Clear? Clear? This? No? Yes? Maybe? Okay? All right. Very good. So this is how it is. Oh, the final component here, the flow rate that is leaving. we don't actually have a flow rate that is leaving, but because of the piston motion, and the positive piston motion is this direction, when the piston is moving that direction, is actually kind of like considered as a leaving flow rate. So that's why this one here have a minus sign here. All right, makes sense? Well, none of this stuff makes any sense. Makes a little bit of sense. A little bit of sense. Makes completely sense. No comment? Yes? No? Maybe? What day is today? Okay.
Wednesday.
Wednesday? Yes, correct. That's correct. Okay, good. Now the flow types. And ready for a first in-class quiz. And you can actually take a look at how is a first in-class quiz. It's already available in a Socrative, and it will be related to Reynolds number, because you know, I'm gonna introduce you two different flow types. So it's either gonna be a laminar flow or turbulent flow. So those are the two flow types. And now the one that defines what is a flow type in question will be related to Reynolds number. So he's already telling you the answer to today's in-class quiz. So just listen to me, we're gonna be good. And we have even chance, thin chance, but still a chance to score 100%. Okay, now the flow or fluid flow, try to equalize the pressure differences. That's like inherent nature of the flow. So if there's a pressure difference, the flow is trying to equalize it. Okay? And then we have two different types of the flows. So it's either the laminar flow or the turbulent flow. Now the difference is this. You know, if I have here a throttle, you know, this is a pipeline or hose line, and I have here P1, and here's a P2, and I'm assuming that the P1 is bigger than P2, meaning that the flow is traveling this direction, because it's trying to equalize the pressure difference. In case of laminar flow, you know, the particles of the fluid, they will travel with a good agreement like this. So there is no disagreement, so everything will be smooth and nice, like this. This is a laminar flow. And in a laminar flow, something that is important for us is that we have to look at mathematically how is a relation between the pressure difference and the flow rate. This is extremely important for us. Very, very, very important. Okay, pressure difference, what's that? How is that we can calculate the pressure difference? Okay, that's going to be obviously P1 minus P2. Okay? Maybe we should even, you know, take the apps here to make sure that we never end up to have a negative value here, but that's a pressure difference. And then we have to relate the flow rate, which is this guy here, traveling this direction, so flow rate and the pressure difference. In case of laminar flow, they are linearly related. So if you make a drawing, I guess that I need to take something off here. So if you make a drawing about this relation, so the relation will be such that I have here, you know, this is pressure difference, this is flow rate, so it always will be linear like shown here. The angle here, that will be defined like what is a particular throttle or the trillings that you need to deal with. But extremely important to understand that this is always linear. In turbulent flow, they are quadratically related. So the relationship is a quadratic. So it will be like this. Okay, so what I intended to do was a second order polynomial. It is kind of second order polynomial, so that's how is their relation. So here I have, this is just something that comes from the geometry, but is a linear related. Whereas in a turbulent flow, the relationship is that I have here something that comes from the geometry, and under the square root I have pressure difference. Those are the big differences, extremely big differences to understand. And then something that sometimes is asked in a written exam is that, okay, what about the particles then? How is it they're traveling in case of turbulent flow? So let's make a pipeline again here. I have here the throttle, and the pressure 1 is bigger than the pressure 2. Oh, it's mentioned here already, and the flow is traveling this direction. In case of turbulent flow, it's not at all in agreement, but there is a lot of disagreement. So the particles will travel such the way, and after the throttle there's a whirlings like this. These are the kind of the paths of the particles. This is turbulent flow. So that you know, for us less important, but relation is extremely important. So this is the turbulent flow, this is a laminar flow, which is what? You know, when typically one is changing from the turbulent to laminar, first of all, very important to understand that the laminar flow, this one here, takes place typically when the pressure difference is small. I know this is a heavy generalization, but you know, roughly speaking, in a mobile applications, when the pressure difference is less than 5 bars, we can make an assumption that then is a laminar flow. If it is more than that, it's a turbulent flow. And of course, it's not moving like this, first laminar and then turbulent. But there's a certain region that is unclear what is what. So it's like mix about turbulent and the laminar flow. But the one that defines which type of the flow is in a question can be defined by a Reynolds number. Reynolds number, that's the one that is very important for us. Okay? And now if you look at the in-class squeeze, it's already question related to that. So take a look at how it's in-class squeeze. I'm actually, you know, Reynolds number defines what's the meaning of the Reynolds number. Okay, type of the flow. So what type of the flow is in the question? That can be defined by defining the Reynolds number. And the Reynolds number actually will be computed depending on your geometry, and it will be compared against the critical Reynolds number. And now it's this simple. So if the flow is assumed to be laminar, if the computed Reynolds number is less than a critical Reynolds number, and if it's going to be turbulent, if it is more than a critical Reynolds number. So the critical, kind of like the mathematically, so top of the flow rate is defined by Reynolds number, simple like that. How it actually goes then? This is the mathematical definition for Reynolds number that you can compute. And now it's very, very difficult to see what is what. Because what's the difference between this and that? One is a kinematic velocity, another one is a velocity of flow.
And up is velocity.
How you can tell?
Because
it looks all the same to me.
I know, because I know this formula.
Yeah, but I must, because you know, these notations are very much unclear. So this is velocity.
This is V d rho over mu.
Yeah, so okay, so yeah, I just need to apologize that the notations that I'm using is not clear. This is V.
Yeah, this V, velocity.
And this is
mu.
mu.
Matching co-resistor.
Mu. Well, they look very much alike. But of course, it's obvious. So of course, we knew that this is a velocity and this is mu, kinematic viscosity. Okay, that's the way you can define what kind of flow rate is in question. For us, it's not that important because it's fair assumption to assume always the flow to be turbulent. There's one tiny problem in the turbulent definition of flow rate because, you know, and it's coming from the mathematics. Because if you have here the pressure difference and the flow rate, so the way it behaves is the curve is like this. And now if you look at closely how it behaves right when you cross it, when it's crossing the zero, it will be the curve like this, like this. Now in a simulation, everything is based on the prediction that is based on the derivatives. And now the problem here is that when you look at the pressure difference here, you know, the derivative associates that will be infinite. It's making very, very difficult to computer software to understand that in case of zero pressure difference, the flow rate is zero. And you actually cannot understand that. That's impossible because it's always using these predictions based on the tangent, and that tangent is infinite in this particular location. So that's why it is very difficult to understand that, okay, in case of zero pressure difference, the flow rate is supposed to be zero. So typically how it is modeled then is that we can make an assumption that in case of very small flow rate, let's say that this is 2 bars, we make this area to be linear. And when it's crossing the zero using the linear curve, that's something that for simulators is very important, very easy to understand. And right when you're off from this zero section, say this is 2 bars or more, then you're following this quadratic curve, second order polynomial. Okay? All right, so main class quiz is this. Reynolds number defines compressibility of the hydraulic volume. We just have been discussed quite a bit about the compressibility, about models and stuff. Is it related to that or not? That's my question. Size of the hydraulic volume? Maybe. When hydraulic volumes become small? Maybe. Then when the flow changes from laminar to turbulent? Maybe. So, let me see how is the situation here. Can you, by the way, see how many online participants we have?
On YouTube, 38.
38. So we're supposed to have more students than 36 because here we have roughly like a little less than 100 students in a class. Less than 100, I said. So then plus the online participants, so we'll see. And I know that it's about time to have a break, but because of the rocky road in the beginning, can we just make a short break today? Because there is so much stuff that we need to cover today. All right? So,
This in class quiz is okay.
so what is it you ask? So what is the success rate or what?
It should be 100.
It's not. No, it's not, because there are 4 obvious choices, so it's very difficult this time. So now you're not sure what to answer. Don't change it. Don't change it. Please, don't change it. Okay, so you all done?
Yeah.
Okay, maybe the online participants, I guess that what they're doing is that they put the YouTube on and they're starting following the recording. At some point of the course, it becomes boring. So then they thought, okay, what about this one particular website? So should I take a look at that? So then they will take a look at that, and my streaming is somewhere in the background. And then what comes out is in class quiz, and then they're completely off. They have no understanding what is the correct answer. Okay, but today success rate will be what?
95.
95. Okay, so the last ones are joining in.
97.
97. Oh, there's a more.
95.
95. No, it's going to be 80, 88. 88. That's my guess. No, you all done?
Yeah.
Okay, not yet. Okay. No. Okay. Better not to answer. Please don't answer. Please. Okay. Well, please answer. But make sure you actually consult your fellow student before you enter your answer. Please. Okay. So now it's just one. Can I click this?
Oh.
Wow!
Okay. Very good. Very good. So it's defining when the flow changes from laminar to turbulent. That's what the Reynolds number is about. It's not about the size of the hydraulic ball. It's not that.
There is this evil person who
Yeah,
makes
one.
me one.
Well, don't know that. Maybe it's me. Maybe it's me. Because otherwise it's going to be yes, sir.
Maybe that one to the
answer causes the 3%.
No, that's not gonna cause. That is not causing it. So it's not that. So it's always it's always counting the answers that are submitted. If not submitted, then it's not accounted. Okay, yeah. So what do you guys say? Can we have a 5 minutes break? And how is my YouTube officer? Is there any complaints about my voice? No further complaints about my voice. Okay, so it's good. Okay, so 5 minutes break, and then let's come back. Let's finalize the flow type, and then let's look at the different components. And the first component will be direction valve. I don't understand this guy. So why is this not cooperating with me? I don't understand.